Okay, we're going to take a look at the odd problems on the take-home test pre-cal. So the first problem we have is they want us to sketch the graph of this function. So what we're going to do is we're going to find the vertex. So if you'll recall, to find the vertex, if we can put it into this formula, this h component here is going to be the x value of our vertex, and our y component is going to be the k value. So if we can convert this quadratic formula into the vertex formula by completing the square, we can solve this problem. So first thing you want to notice is that x has to be a value of 1. So if the leading coefficient of A, you have A, B, and C, if A is not 1, then you have to factor it out. So we're going to group up the x's, and then we're going to extend the C out. We're just going to push it out. So we have x squared plus 6x plus 12. And since there's only a 1 there, all we have to complete the square is take half of the b term, which is 6. So half of 6 is equal to positive 3. And that's the number we're going to use to build the perfect square. And that equals 9. So we're basically going to insert 9 on this side. And we just added 9 to the equation. So we're going to subtract 9 over here. So that keeps the whole thing balanced. And then we're going to go back and just build the square. So we use x plus 3, and that 3 always matches up this value here. And then we have 12 minus 9 is plus 3. And the a value is, of course, 1, since the coefficient was 1 for a. So what does this tell us to do? Well, this gives us our coordinates for our vertex, and the x value, it's not positive 3, it's a negative 3, because if you put in a negative 3 for x and add it to 3, it takes you to 0. So we're going to go over to negative 3 and up 3. Oops. And we're going to put our vertex there. And since we're not really too concerned with the accuracy of this graph, we know we're going to have a parabola that's facing up, because that's a positive 1. So just sketch yourself a parabola that goes up like this. Okay? Alright, so just make sure that you realize that this is the vertex formula. And it's completing the square is what we did. Okay, let's move on to the next one. The next problem has an imaginary number here, and we're going to use the property that I squared is equal to a negative 1. And what it means to simplify here is that we basically don't want that I in the denominator. Just like you don't want square roots in the denominator normally. So to get rid of this, we're going to multiply by its conjugate. So if it's an addition, we're just going to multiply it by subtraction. And we're going to do the same to the top. And when we do this, we're going to have to FOIL the bottom. And hopefully you are starting to recognize these patterns pretty quickly, but when you have basically the same term, and the only difference is one's addition and one's subtraction, and the middle terms cancel out when you FOIL it. So you have a negative 1 times negative 1, it's a positive 1. And then when you FOIL the negative 1 all the way over to the negative 10, you get a positive 10i. And when you FOIL the inner terms, you get negative 10i. So that's always going to be the case when these completely match up. So 10i, sorry about that. And then when you FOIL the last, when you multiply the last term by the last term, you get, in this case, a negative 100i squared. Alright, and of course, these two things will cancel out. And then you go on and FOIL the top, or not FOIL the top, but distribute the top. So you have a negative 6, and you have a negative 60i. So remember in this fact that I just reminded you of, that I squared equals a negative 1, we can replace the bottom by 1 minus 100 times negative 1. And on the top, we have a negative 6 minus 60i. What's common about those two? They both can be divided by 6. So let's factor out a negative 6. And that'll leave us with 1 plus 10i. And then, of course, we have a negative 100 times the negative 1. So we have 1 plus 100. And we have a negative 6, 1 plus 10i on it. So that's about all you can do to this problem. Just remember that this technique will get rid of anything in the denominator if it's in the form of addition or subtraction. Alright, now number 5 is pretty easy. Just want you to factor it completely. Okay, well, all we have in common is that we have an n in there, right? So if you take an n out, you have n minus 8. So that was a fairly easy problem right there. So moving on to number 7, this is sort of trying to guide you into recalling how to complete the square. So they basically want to know what value, what number we need to add to this problem to make it a perfect square. So recall that that's a and that's b. So a is equal to 1 and b is a negative 1. To complete the square, you always take half of the b term. So half of a negative 1 equals a negative 1/2. And then you square that value. So if you square the top, you get positive 1. And if you square the bottom, you get a 4. So the answer here is 1/4. So if you wanted to complete the square on this, which they're not asking us to do, but it would just simply be y minus 1/2 squared. Now if you take the time to FOIL this out, it'll take you back to this portion of the equation. Alright, so that takes us to number 9, which is basically complete the square. And not only complete the square, they want you to solve each equation. In this case, we're going to solve for p. So, one thing we can do is we can move this 47 over, negative 47, by adding 47. And if you do, the right side is now equal to 45. And you're kind of lucky on this one because the value in front of the square term is equal to a 1, so we don't have to factor anything out. Let's get this over. Alright, so we're going to do the same thing. We're going to take half of a negative 12, and that equals negative 6. And then we're going to square that, which gives us 36. So basically what we're going to do is we're going to add 36 to the left side, and we're going to add 36 to the right side, and that right side looks like it's going to give us 81. And now the left side can be rebuilt by using this half of that b term. So we have p minus 6 squared. Well, since we have everything on the left side squared, we can solve p by taking the square root. And when we do that, we have to do it to the right and the left. And just recalling that when you take the square root of a number, it's a positive number, the result is going to be both positive and negative, 9 in this case. And the left side, of course, cancels out. So this is going to leave us with two answers. So we're basically going to add 6 to both sides. And we're going to get that p is equal to 6 plus 9. And the second root, or the second solution, is p is equal to positive 6 minus 9. So of course that's going to give us 15 and negative 3. So p is equal to negative 3 and p is equal to 15. Alright, let's take a look at number 11. It's one that you might have not recalled, but it's we're going to look at the sum of cubes. Alright, and let's take a look at a simple problem first. If you have x cubed, let's say plus 8, and if we want to apply this rule of the sum of cubes, and let me just go ahead and give you the rule here. If you have a to the third power plus b to the third power, these are of course both cubes, right? So the simple formula is a plus b is a factor, and then this middle term, or the second term over here, is simply written like this. And the middle term is going to be product of a times b. So notice what happens here. These two things match up, and over in the quadratic that you factor out, you'll get a subtraction, so the sign is the opposite here. And the same rule applies for differences of cubes. So if we have a to the third minus b to the third, the first factor remains the same sign, so you subtract in the quadratic. Looks like this. And now we change this to addition, and that formula holds true. So is this a perfect cube? Well, of course, x to the third is x to the third, but is there some number, and let's not use x, let's use n times n times n, that equals 500? Well, I don't see one right away. Let me stop the video here, and we'll take a look at the second problem and see how that looks. So I want to keep this video under time, so I'll go ahead and stop it here, and we'll pick this up in a second.